Right, so hello everyone. I think we can start now. I think some students are already joining. So is my audio fine?
Yes.
Great, thanks for confirming. So a couple of things actually before we start. So regarding when you write me an email, I will prefer if you use my email ID instead of using the web courses. I mean, of course, web courses is also fine, but just in case if you have a choice, direct email, I think you will get a faster response. And the other question I have for you guys is, I see like some of the students were joining like the Zoom link from the lecture for the office hours. And I still see like some students are trying to join the lecture using the office hours link. So is there any confusion regarding that, like any trouble to find that link? Some way we can fix that? Because ideally, I think if you are using a calendar, those links should be there like in your schedule, right? And you can use it. So any student like right now, which is having any difficulty? Okay, probably students who are having difficulty, they have not joined. Anyways, that's good. Now let's continue. So in the previous lecture, we were talking about, and again, this is like continuation of what we covered in the last lecture. And we will start with like a different computer vision task, which are like kind of an open research problem. Okay, so the first and most important, I think, very well researched is object recognition. So let's first try to understand what object recognition is. So the idea is, let's say if you have an input image. Now the question we want to answer is, does this image contain like any category of object or any class of object? And that class could be like just say a person. So the question could be like if a person is present or not. So if that's the question, then we can say that, okay, it's person recognition or person classification. But if it's like a general object, we can say object recognition. And one point I would like to add is recognition and classification. You can use interchangeably, perfectly fine. Both are used for the same thing. Okay, so sometimes you might see that I'm using classification, sometimes I'm using recognition. Both means the same things. Okay, so let's see some examples. So these are some example images, and we can solve this task as a human. And the problem is, let's say, person recognition. So we want to say whether a person is present in this images or not. So you can see like in all these images we have so a lady standing here, we have two footballers, we have a guy here, and again in this one we have a person like sitting on the railing, and three guys here, right? So the answer is yes. And so you can see that like a lot of variation here, right? Just one person, and in the background you have a crowd as well, and you can see like different context and again different resolution. So in this case, like we are just looking at the person. In this case, there is a lot of other context as well. These two big trees, and the person is too small or too tiny. And the other thing you can observe is that these guys are like performing different activities, right? She's just standing there, he's talking on phone, carrying some luggage, and again just sitting there playing football. So different kind of activities. But if we just look at the simple problem of person identification, then we just need to say, okay, person is present or not present. We don't care what that person is doing and what's the resolution, like how big the person is or how many person are there like in the image. So all of that is irrelevant. Now, similarly, I will show you these images. And again, the same question, does this image contain a person or not? And the answer is no. All right. So the question, like it's a binary question, the answer will be either yes or no, and that's called you can also call that binary classification. And of course, if you have multiple classes, we will talk about that in later as well. So you can have like, let's say dog or maybe a plane. So if you have multiple classes, then again, that will be object recognition, but the problem will be not just saying yes or no. You will have to say, okay, whether person is present or not. So yes and no will be corresponding to each object category. All right. So that was, so I think there's a question. Can you share your slides for the lecture? Okay, I think I forgot to share that. Sorry about that. So let me quickly, just give me a minute. No, but these slides are, they should already be there, right, on the web process. Probably that's why I didn't share. You should have these slides. So who asked? So Sayed, you don't have these slides? They are already shared. I can actually share these slides with you on Zoom. But I think if you check your web courses, you should have these slides. And they're also available like on the course web page. Okay. So comment from Daniela, they are in an announcement, not files. No, but if you open that, if you open that web course link, in that link, you will find that file. And there was an announcement, I think, before the last lecture when where I shared the file as well. So it should be there. So is that fine, Sayed? Do you have the slides now? And Daniela? So I think there's a question from Fernando. Okay, great. For multiple labels, what would be the best way to handle an image that doesn't fall in any of the labels, like is cat or dog? Yeah, we'll talk about these things later. So let's first just try to understand like what are the problems, how to solve these problems. We have like the full course to address that. Okay, so I will defer this question for a later lecture. So can you guys see my slides? Okay, great, thank you. Okay, so that was object recognition, where we were only interested in saying that whether a particular category of object is present in that image or not. Now, the second interesting problem, which is also highly related to object classification, is object localization. And another name which is highly used is object detection. So both are similar things. So in object localization, we do have to say whether that object category is present or not. And in addition to that, we also have to actually localize where exactly that object is present in that image. Right. So you can see the examples here. For this case, you can say that we have, you can see that we have this bounding box around this person. And similarly for all the cases. Right. And of course, you can have multiple instances of the same object, or you can have just one instance. For example, in this image, we only have like one person, right? So one bounding box. And in this one, we have three. And although we have bounding box for one, but ideally we should have bounding boxes for the other objects as well, like in this case. Okay, so this is object localization or object detection. And similarly, like let's say if you're just focusing on humans, again, just one category. So these are some examples of human detection, or you can say person detection. You can see that there are multiple people walking around here in the scene. So you have to detect all of those. And detection is like maybe drawing a bounding box. And later we will see that it could be like drawing the fine boundary as well instead of bounding box. So that I think is the next problem I'm going to talk about. So, and you can see here that sometimes it's very challenging. So in this case, you can see like these two guys, it's kind of overlapping, right? But you still have to say where it is. So this is a more difficult case. We call this occlusion. All right, so that was detection. Now the third, and again, this is correlated, is semantic segmentation. And semantic segmentation is for each pixel in the image, you have to say, okay, which class this pixel belongs. All right, so you don't care about like the full image, you care about each pixel, each and every pixel. I think there is a question from Momal. What is the difference between detection and localization? Yeah, as I said, both are like same, localization, detection. You can use them for the same thing. Okay, so semantic segmentation, as I said, each pixel you will say which category this belongs to. And here you can see that the same image, I'm just showing as a smaller resolution. And here you can see that if this is green, so this is kind of grass, this color, and this color is for water. So you can see here that for each pixel we have a color, and the color is actually just indication of which semantic category this pixel belongs to. So we can have, for one object category, we can predefine a color, and we can just use that. All right, so that's called semantic segmentation. And you can have like segmentation at a higher level. So again, this is the same thing, just describing what the semantic categories are. So this is sky, this is tree, grass. Now, what you can do is you can actually go one level up, and you can describe like each semantic category, not just say, okay, this is grass. So here you're describing, for example, this person feeding ducks in the park, right? So that's more informative, more descriptive, describing what's happening in the scene. And again, it's not just saying that a duck is present, it's saying that duck's looking for food. Okay, and so for that mean you need all this contextual information. In fact, like to solve this. And so this is like some results, not recent, 2017, and you can see that what we can solve. So this is like the ground truth. Ground truth is like what exactly it should be in reality. For example, in this case, this is the semantic map where this green says like it's a grass, this one is like the sky, and this says it's a cow. And this is something like which can be achieved. These are just two different methods. This is fully supervised, this is semi-supervised. You don't have to worry about what this is. It's just showing that, okay, how much we can do today. And again, this is 2017. We can of course do much better than this. A question from Ruchia. So through pixel color, can we identify the semantics? So the pixel colors are just for the for visualization, so that we can understand, okay, this pixel belongs to this category. So we have like manually mapped each semantic category to each color, each pixel color. Is that your question? Okay. So I mean, you can use any color you want. So it will not change like the outcome. You can say, okay, grass. You don't have to use green. You can use black as well. Then whenever there is black, we'll say it's grass. Okay, so you can tie like the color to semantic meaning. So question from Momal, what is FG object class in the 2017 work? Copy this one. So I didn't get, what is this FG object, Momal?
Professor, so there is a class.
Oh, okay, the label. Yeah, I see
colored,
that.
yeah. So what is this?
FG
like figure object
is,
or something?
Yeah, so that's like foreground object. I think a shortcut for foreground objects. In this case, it's cow.
Okay, great, right.
So in this case, these are like a people. So that's the foreground. So the main object like which is present in the image.
Right. Thank you.
So yeah, so Alina answered that question, foreground object. So Anshuman has a question. In semantics, the processing is based on the information in neighboring pixels, or every pixel is treated individual even for the processing or detection part. So that's a very good question. And of course, you can't determine the semantics just by looking at each pixel independently. You need the context. And that's not just true for like AI algorithms, that's true for you as a human as well. If I just show you a pixel, let's say of this car, it's just a black dot, right? There's no way you can say that this pixel is coming from a car. So of course you need the neighboring pixels and all the context. And that's what we do like when we develop an algorithm as well. So that's a really good question. Okay, so now another interesting problem is, which is related to semantic segmentation, is semantic part labeling. So this is like more in depth. So we are not just saying that, okay, person is present in a pixel. We are describing each pixel as like different, giving it a different attribute. So in this case, you can see we can distinguish like cap, we can the hair, like the face, and whatever clothing there is, right? So it's like more detailed version of semantic segmentation. Even we are differentiating between left and right arm. So this is really interesting, face recognition. And I think most of you might know that today we have like very, very good algorithms to perform face recognition. And it's much better than what we can recognize, what we can achieve like as a human. So there was a question in the last lecture, like, is AI better than human? So this is like one problem where AI has advanced a lot, because as a human, mean, if you have to perform face recognition, one image, two image, three image, it's fine. Or one video stream, two video stream. But if you have like million of images or multiple video streams, I mean, you can't do it, right? It's too tiring. So your brain will not be able to process that. But the algorithm, mean, not just it can like identify it correctly, it can also do it at scale. So face recognition, it's simple. Given an image, you have to say that, okay, this face belongs to which person or which subject. All right. And again, there are different variations of this. So it could be like, you can solve this as a classification problem. And the way it will work is, you will have a set of subjects, let's say 100 different individuals. And for each individual, you might have an ID or a name. So then your algorithm, what it will do is, given an image, it will try to assign that image to one of those subjects. Okay, so that's like classification, but again, face recognition. The other variation is kind of, again, it's face recognition, but you can do that as a retrieval. And retrieval is something different. So in retrieval, what will happen is, let's say you have 100,000 subjects, right? And you might have 100,000 different images. So your network will not classify that image to be one person. It will extract some features. And in the last lecture, I think there was a comment from one of the students, I don't remember the name. So he was talking about latent features. So, right? So the network will give you latent features, which you can use to actually match against all the images you have in your gallery. So that's called image retrieval. And then based on that matching, you can say that, okay, this facial image matches to this facial image, and then you can recognize that person. So that's another variation of face recognition. So, and again, this is like another variation. This is open universe face identification. So an interesting question could be, given in this image, can you recognize like a important figure? So we know, I mean, this is Barack Obama, right? So we can identify that, and we'll have to ignore all the faces in the background. The other could be like, if it's a social network, and if you are like one of the person standing in the background, then you might be interested in these faces as well. So then you might want to identify these faces. All right. So different applications, but again, it's all face recognition. So this is another variation where you have like all a large set of images, and you have to find images of these, let's say, particular subjects. So this will also be like kind of retrieval problem. You have to do matching, but at the end, it's all face recognition. Okay, so in similar lines, another interesting problem is facial expression recognition. So can you identify like what's the facial expression given an image? Okay, so you're not interested in the identification, but how that person is feeling. So it could be like the person is sad, the person is smiling, he or she is happy. So again, that's kind of classification problem, because these different expressions are like different classes, right? So given an image, you have to classify them into one of those categories. So at a high level, you will see like later on, most of these problems will fall into classification category or recognition category. It's just like different applications and different setup. And this is like very interesting application of fatigue detection. So when you're driving a car, then it's a very, if you're on a long drive, then you might be like very tired. So if you put a camera and try to identify if you're falling asleep or something, so that can be very, very useful. Okay, so it's trying to detect whether you are fit enough to drive or not. And this is another interesting application, which is lip reading. So by just looking at the lip, can you recognize like what that person is saying? All right. So in this case, it's a bit more complicated than classification, because the input is, first of all, it's not just image, it will be a sequence of image, which is a video. And then you will have to convert that into textual format. So the input is video, but the output will be text, or it could be audio, depending upon like how you are trying to solve this. So it's much difficult when you compare this with classification. And of course, we can have very dense crowded scenes, and we can try to solve different problems in these type of scenes. For example, we can try to identify like the flow of the crowd, where it's moving, the density of the crowd, right, and the activity which is being performed in the crowd. And of course, we can count. So, and this is really interesting. Again, there was a question in the last lecture where one student was asking like, is AI better than human? So this is one problem where if I give you this image and ask you to, okay, count how many people are there, you will sit there for hours, right? Still, you might be inaccurate. But if I ask a computer algorithm to do that, it will do that instantly in microseconds, right? Or milliseconds, depending upon how fast the algorithm is. And these results are like, and this is not latest one, this is 2015 or 2016. So the ground truth is like 634, and the algorithm was able to predict 640, so pretty close. And it can be more denser. So in this case, we have 1428, we can predict 1468, even more denser. So around 2,300 people here, right? And the algorithm can predict 2,496, which is pretty close. So this is also very interesting. Now, a bit more complicated, this application is visual business recognition. For example, if I give you a video or let's say an image and ask you to detect attributes like, okay, what is this place, or what is this shop about, and where's the location, and ask you to describe all these things. So this of course involve not just computer vision, it will be like more of a multimodal approach. You will have to use many other modalities. For example, the geolocation, and let's say the timing information. So, right, so biometrics, again, a very good area. We already talked about face recognition, which is part of biometrics, but you can have a lot of other things as well. These days, like fingerprint, mean all of you have that in your phones, and it works pretty well. So it's a matured area. Smile detection, again, you need this in your cameras when you're taking photographs. You have a lot of video games which you play, which is making use of vision. All right, so these are different examples for that. Okay, so most of the problems which we talked about so far, they are like for images. But what about videos? So videos, if you think about this, it's just sequence of frames, right? And usually the standard is 30 frames per second. It could be higher, it could be it could be lower. These days, it's usually at 30 fps. We hardly see lower than this, but we might see higher than this. So what 30 fps means is, when you play that video in 1 second, there will be roughly around 30 frames. Okay, and it's kind of optimized like for human vision, because when you watch a video, then that's the rate which you can easily process and identify like what's happening in the video. So this was like the video playing, and these are the frames from that video, and these are like sampled, not all the frames. So you can see that how they're changing over time, right? How the face is moving. Now, by looking at each frame independently, it's hard to see what's happening in the video. But if you look at this video, then it's easy, right? The person is just smiling and moving, but from the images, we can just see, okay, person is smiling, but we don't see the motion. So for videos, like this is one data set we have, UCF101, it's very popular. And the problem we are trying to solve here is action recognition. So this is similar to object recognition in images, but instead of images, we have videos. So in videos, we have actions. So given a video, can we recognize what's happening in that video? All right. So for example, this is cycling. So can the AI algorithm, if we pass this video, can it determine like cycling is happening or not? Okay, so that was like analogous to what we saw for images. And again, we had object detection in images, right? Similarly, we can have action detection in videos. So in this case, you can see that this is a surveillance clip, and we are trying to not just localize or detect these individuals here. We are also saying that, okay, what activity each individual is doing. So by the way, this is like output from a real system we have developed. We have a patent for this. And you can see that it's trying to identify all the people, and it's also saying what activities they are doing. Of course, I'm not showing the type of activities. So activity detection is, first you have to say which activity is happening. So that's action recognition. And in addition to that, you will have to localize exactly in the video where that activity is happening. All right. And this is more complicated than action detection. So this is video segmentation, again, similar to image segmentation. In this case, you don't just have to like segment one frame, you have to segment like all the frames in the video. So these are again examples from a real algorithm which we have developed. You can see that we are able to segment like these fishes pretty nicely. Even if there's some overlap, there's occlusion, we can recover those detections. So vision is not just about like trying to estimate or trying to determine what's happening in the video. It could be much more. For example, in this case, I'm showing you, if we have a video clip, for example, this one, where some kind of action is happening. All right. So now the problem is, given this video, can I synthesize a video which is describing the same action from a different viewpoint? For example, this. Okay. So we have developed this algorithm recently, which if you give this image as input, it can actually predict this output. So this is a different viewpoint. And of course, it's not perfect. There's a lot of blur, but again, it's a very hard problem. And these are just initial results. Okay, so again, this is not estimation. It's kind of, you can say, video synthesis. So a question from Fernando, how did it make the background? So for the background, we just pass like one image, which it will utilize to render like all the scene context and everything. So the main task is like to transform this action like from a different viewpoint. That's actually a good question. All right. So this is video synthesis. Now, these are some samples like, and again, this is detection. We're trying to detect vehicles, and these are not ground videos. These are aerial videos. So capture from above the ground. But again, the same problem, vehicle detection. And you can see that like how this is much different from what we were seeing like when we were seeing the videos from the ground. So by just changing the viewpoint, how the complexity of the problem is changing. And this is also another interesting problem. This is called tracking. So what you have to do here is, given an object, so you will have a video. What you will have to do is track that object in all the future frames in that video. Okay. And of course, there can be multiple objects. And if they're crossing path, so that's the hardest thing. There is occlusion, then still you'll have to try to recover, okay, it was the same object and continue tracking it. So these are just sample results from a real algorithm, which is tracking these vehicles. And a question from Daniel, how does it manage to keep track of one object without a moving camera? So I don't get it. What do you mean? I understand like you need a moving camera to follow that object, but even if you have a static camera and an object is moving, you can still track it, right? So Daniel, okay, with the moving camera, wouldn't every object be considered moving? Right. I mean, if you're moving a camera, if you look from camera perspective, every object is moving like in the pixel space. But in real world, if you look at the context, it's not moving, right? I'm missing your question. So it doesn't matter whether a camera is moving or not. You can perform tracking in both scenarios. And to track an object, that object, it could be stationary as well. Even if it's not moving, you can track it. It's just, it will stay at the same location. So we'll come back to that, Daniel, if it's not clear. Probably you can try to rephrase that because I don't think I get your question. I think another question from Sanyang, what could we do to check if a video is synthesized? Check if a video is synthesized. I didn't get that question either. You mean like to evaluate if the video is synthesized or not? What do you mean by you want to check it? You can just watch that video, right? If it's synthesized, you will be able to see it. And
I think he means to be able to differentiate it if it's fake or not. Yeah, the deep fake videos.
Okay. How could we do check? Yeah, that's an open research problem. And again, that's a classification problem, right? So you can train that as a binary classification problem where you have fake videos, real videos, and then your network can determine like if it's real or fake. And like what exactly should the algorithm mean? I don't think we are in that stage yet to answer that. But at a high level, that will be a binary classification problem. Okay, so Anshuman, for any action-based problem, how do we decide the duration of video that will be analyzed for action recognition? So the way we solve action recognition, usually it's like there are different variations. So one is called like trimmed video. So in that case, we exactly know like the video is starting when it's ending, and we only send that clip to the video, and then it will say, okay, which action is happening. The more difficult case is when you have a long video, which is kind of untrimmed. So that's a technical term, untrimmed, where we don't know when the action is starting, when it's ending. So then the task apart from action recognition is to localize that action in the temporal domain. So we'll have to say, okay, at this time the action is starting, at this time the action is ending, and this is the action. So that problem is called temporal action localization, and it's kind of a middle ground between action recognition and action detection. Right? Because action detection is spatiotemporal detection. You say when it's starting, when it's ending, and also like in space where it's actually happening. So I hope I answered your question. Then Daniel, with the moving camera, I think we covered that. Question from Rajat. Ideally, all persons should have.
You're saying that from Anshumans, you are saying that for a long video, we should first we should determine where the action is happening, and then we try to classify the action, right?
Right.
Yeah. Okay.
Okay, question from Rajat. Ideally, all persons should have same representation in latent space. So how do we manage to match trajectories of different people across images? So all person will not have same representation, and that's the key. So for example, like if you're doing person recognition, right? If all person have same representation, then how will you differentiate between those two? But you still can differentiate, right? Which means that the representation is not same. And again, that's just one aspect which is used in tracking, where you look at like how that person is looking, what's the appearance. And apart from that, there are like a lot of other factors like what's the speed of that person, what's the location, where it's moving, the direction. So all of those factors are used when you track. All right, question from Mobile. An object can be moving in field of view of a static camera. Right, that's true. So that was a comment or a question, Mohammed? Talking about DVR that we covered. All right, so I think there is no other question. If any question was not answered, please let me know. So I think the only question which was not answered is Daniel's question. So Daniel, you want to rephrase it? You can use your mic if you want.
Yeah, so if we had a static camera, it's easy to see a moving object. That's simple. But if the camera was itself moving and say there was a parked car, if the camera itself was moving, wouldn't that parked car be considered to be moving since the camera's moving?
Yeah, from camera point of view, yes. But yeah, I understand what you're saying. But I mean, in reality, the car is not moving, right? It's just moving in that pixel space. So, and then with that car, all the background pixels are also moving, right? So then you can infer that, okay, if the whole context is moving, then the car is static. And again, as I said, it doesn't matter whether the car is static or not, you still can track it. It's just like the track is not changing. I hope that clarified your question.
Yeah.
Okay, all right, great. So let's move on. And again, this is a more complicated case. And here, one thing you can see is that even if the car is going under the bridge, it is being tracked again. Right, so this is, I think, answer. I think Rajat asked or someone asked, the appearance will be almost similar. So in this case, it's actually similar. All the cars will have similar features, right? Because we can't see the texture, it's very far away, but still we can track it. And the reason is like the location, the speed, and a lot of other factors which are being used. And again, this is like algorithm which is giving these detections. Okay, so a question from Sean. Are we going to be implementing some of these topics we have gone over so far in our, not these, but I think the basic ones, like you will do classification. So a lot of variations in classification, but these are like, I think, very complicated problems. So out of scope of this course for you to implement, but we are going to talk about like how detection and all that is done, but it will not be given for assignments. But of course, if you are interested, you can pick like these problems for your projects, and then we can help you in that. Okay, so question from Sanjay. Will the action recognition still work if there are multiple persons doing some action? I feel individual person are to be detected first, then the action has to be recognized. Yes, that's true. So again, there are different variants for action recognition. You might have just one person performing the action, which is the easier case, but again, you can have multiple persons performing the action, like the video I showed, right? There were multiple people walking around. So then you have to localize that person and then recognize what that person is doing. So that's correct. Question from Stephanie. So is this what we would be in classes like advanced? Right. So these are like, if you want to do coding and all of these topics, it's like advanced computer vision. Okay. So a very practical application is video surveillance and monitoring. So video surveillance, it seems like one application, but you will see like all the problems which we have discussed so far, all of those are involved. All right. So surveillance starts with detection. Even before detection, it's classification, whether the person is present or not. Then we detect that person. Then we have to track that person, right? So object tracking is involved. Then object categorization classification, we classify, we try to re-identify the person, if it's the same person or not, if we are looking at the person from multiple cameras. All right. And then again, recognizing event or activities in the video stream. For example, what action that person is performing. Is he like planting some kind of bomb, or is the person just sitting there, or like multiple people are talking? So recognizing all those activities. So all of these problems are required if you want to build a video surveillance system. Okay, so that was a lot of talk about what different problems we can solve in computer vision. But let's try to understand like how this detection works when we have to detect this object in an image. And we will go through like a very simple solution, which is called template matching. Right. So let's say, for example, we want to detect a chair, and this is the chair. And the problem is we want to detect this chair in this input image. And you can see that this chair is perfectly matching this one. As a human, we can easily say, okay, it's very trivial. We can just localize, okay, the chair is at this location, right? But for a computer algorithm, it's not that easy. So let's see how we can come up with a very simple algorithm for this. What we can do is we can start from this location and try to match this chair with this patch. Okay, so this is like template matching. This is the source template, this is the target template, and we can just match pixel wise. If each pixel is matching, we say it's a match. If it's not matching, we say it's not matching. All right, and then we can do that for all the locations, possible locations in this image. So this approach, it's called sliding window. So you put this bounding box starting from this location, and all the possible locations keep moving. So the step by which you are moving, that's called stride. All right. And the size of this window, that's called window size. So you keep moving right, and then you shift one column, one row down, and then keep scanning. So this approach, it might be like very trivial. You might be saying, okay, this seems very simple. But later in the course, you will see that in most of the algorithms, this approach is being used, even in like the latest algorithms which we have these days. So this sliding window, it's very effective. Okay, but this is very crude form. So then what will happen is, if you find that correlation, like matching each pixel, you will get a map like this. All right. So if the color of the pixel is white, it means that it was matching perfectly, very high correlation. If the value of the pixel is kind of dark, close to black, it means that it was not matching at all. So you can see that starting from this location, it's not matching that well, but at this location, it's very highly active, right? Which means that the chair is present at this location. And that's the solution. So with this very simple approach, you solve the problem of object detection. So it wasn't that hard, right? So question from Steve, how do you account for scale in sliding window technique? That's a very good question, and we have a lecture like just covering that topic. So I will hold on to that. A question from Sarat, does this name approach has stride 1 and window size equal to chair image height and width? Yes and yes. So it's a stride 1, and the size of this bounding box should exactly match with this chair. That's why you will be able to find the correlation, right? You should have that correspondence. So Steve, that's a very good question. As I said, we have a like complete section where we're going to talk about that. So this seems pretty simple, but let's see like whether this is really working or not. Is this realistic? So let's pick another image. And again, we have the same chair. So again, we have to detect the chair in this image. As a human, we can say, okay, this is a chair, this is a chair, this is a chair, right? Pretty easy for us. But let's try to use the same algorithm which we developed. And this is the correlation map which you will get. It's not working, right? It's saying all these are chairs, which is not true. So why it failed? So one reason was the scale, which Steve said. The scale might be different in the source image and the template you have and the target image. And that's like just one aspect. But if you look carefully, like even the template is not matching, because the texture of this image or the shape of this chair, it's entirely different than this chair. But we know this is chair, this is chair. But if you match pixel wise, it's not going to work. All right. So then how we can improve this? Again, very simple solution. I think question from Alina, we can do image scaling, rotation, etc. to find the chair. Yeah, that's true. We can of course do that. We'll come to that when we talk about object detection in more detail. So these are just like very rudimentary algorithms, just to give you an idea of like the flavor of the problem, what exactly needs to be solved. Because before you jump into like what should be the solution, you should try to first understand what is the problem, what are the challenges. Okay, then it's pretty easy to understand the solution. Okay, so instead of matching the raw image pixels, what we can do is we can try to use something more sophisticated. Okay, so we can try to extract some kind of features. And we have a couple of lectures in just extracting features, and we'll talk about what features are. But just to give an idea, I mean, these features could be just edge features, what kind of edges are present in the image. These could be like just color histogram, what kind of colors are present in the image. Again, gradients, and these are like some different kind of features which we're going to talk about in this course. So we can use these features and then perform matching. All right. So another interesting idea is a bag of words representation. Again, this is a concept which can be used in different contexts. So in this case, what it's saying is, let's say if you have this input image, so instead of matching pixel wise, what you can do is you can actually try to segment this image into different patches. And these patches are shown here. You can see that necklace, you have eye, you have nose. And don't ask like how we create these patches, but just try to understand the idea. So once you have these patches, then you can create a bag of this. So that's why it's called like bag of words. And these are like all different words, like semantics from this input image. Now, once you have this bag, then it will be easier for you to perform matching at a later stage when you have a face which is like from a different viewpoint or from a different person. Because then what will happen is you will extract similar bag for that person, and you will find like lips, you will find hair, you will find nose and eyes, and then that matching will perform much better than if you try to just compare pixel wise. All right, so this is like a very good concept. So how you can extract these patches, one interesting idea is you can learn these code words. And again, these code words could be just edges in the input image, or these could be like some other high level features. And you can just count these features from the input image. So this is a histogram. So for those who don't know what a histogram is, if these are your code words, histogram is just count of these code words, like how many times these code words were present in the input image. So just the frequency of those items. All right. And again, this is a way to represent your features. And later we will study like how histogram of gradients and all those features use this strategy, where we will create histograms and then we'll perform matching. Okay. So then the standard pipeline for this kind of task is you first extract features. You can get like, for example, histograms, and then you train a classifier. We'll talk about what a classifier is, which will tell you, okay, whether the object is present or not. Right. Again, this is just showing you bag of word representation of different faces, and you can see that if you have these kind of things, you will just match, okay, eyes present, eyes present, eyes present. Then you can match, okay, this is like a bag for face. Okay, so I think we talked about this like computer versus human vision, but let me try to like give you the technical aspect, like which task will be performed better by computers and which task will be performed better by humans. So sometimes computers are superior, sometimes humans are superior. For example, I showed you this image earlier, and if I ask you to count a number of people, I mean, it will be very difficult, challenging for you. Of course, you will be able to do it, but you will have to spend a lot of hours. So this kind of tasks are easy for computers. So if you want to differentiate like task technically, then if the task is global, all right? So global tasks are like, for example, if you have this image and I ask you to segment, let's say this plane, all right? So then as a human, you will be able to easily figure out, okay, this part must be belonging to this object, and you will draw this boundary, right? So that's kind of a global task. But if I give this task to a computer, I mean, it will just match the appearance of the pixels and it will fail to recognize, okay, a plane has this kind of shape, and it will miss this thing here, right? And it will draw a boundary like this. So this is kind of a global task, drawing the boundary or describing the image or giving the semantic meaning what's happening in the image. So those are kind of global tasks which requires a lot of context. So in all those tasks, humans are much better than computer. But if it's a local task, and local task is like, let's say, just grouping these pixels based on the appearance. So computers can be very efficient. It can easily match like the features of these pixels, right? And it can group them like this. And the example I showed you earlier, like counting people, it can easily extract features from those locations and say, okay, it's a person is present, and just count that. So those kind of local task computers are much better. And again, like recognizing face maybe in very crowded scene, it might be hard for us, but for computer, it might be very easy. Okay, so let me conclude this lecture by like going 50 years back. So 50 years ago, like if I show this image to like the computer systems we had that time, clearly it will be like kind of out of memory. We didn't have power to process these kind of images. And I think there's a question from Rajat. For matching two bags of n size each, won't the complexity reach? Yeah, that's true. And ideally, your bag, when you create your bag, it doesn't have a lot of items. So you will try to control that n so that it's like still tractable. Okay, that's a good point. So images like this, it will be out of memory. And again, if 24 years ago, I would say like perform object detection. So the algorithms could do something like this. It will say this is car, this is bird, this is dog, right? We didn't have that fancy algorithms. And this, you all know, like facial recognition, we had these 15 years ago in our cameras. And this is 5 years ago. We can count like how many people are present in this image, which is pretty exciting, very challenging for humans. And today you might be seeing something like this, which is too advanced, right? Where I think you're not able to hear the voice, but you can see like the face swap and all those things, right? And it's pretty realistic. So you can create videos where you use like audio from someone else and ask like a totally different person to say those same words in her voice or in his voice. So that's totally possible. And even like human can't recognize whether this is fake or not. Okay, so there was a comment earlier like how to do that. So that's an open research problem, very challenging problem. So I think this should be the last video I'm going to show you. So I'm showing you to just observe this. This is a police chase. And I want you to think about this when the police is chasing the suspect and they're trying to solve this problem. So the problem is to catch this person. So think about what are the different computer vision problems which are there in this video, which can be solved using AI and which can help the police to catch the suspect faster. All right, we have already covered like a lot of problems in computer vision. So let's see like how many such problems we can see in this video. So starting from here, you can see that they are chasing this car, right? So first of all, I mean, if we don't have like a actual person there, if it's just a computer, it will have to say, okay, a car is present or not, right? So that's object recognition. And then the next step will be detection, like, okay, where exactly the car is present in the image frame. So that's two problems, right? And then we have to track this. You can see that there are a lot of occlusions. It's going behind other cars, and you will see like a lot of other cars with the same texture or maybe the same model as well. So then the AI will have to track this car. Okay, so very crowded scenes as well. And then you can see that, okay, now the car is far, far away. And this is again a very challenging problem. So if you have a very low resolution, still you will have to extract some meaningful features so that you are able to track it. Okay, so let me move to the interesting part. So now later what happens is, again, I mean, you can see it's hardly visible. As a human, we can't, but I think I'm sure if we use an AI algorithm, it will still be able to track this car. So later what happens, the guy parked the car here and he ran into the forest. All right. And the guy is completely invisible. Now, how computer vision can help here is you just have this video stream. You can see even if the person is present, he might be like hidden behind the trees or the bushes, hard to see. So later what police did is they tried to use thermal sensors. And then they were able to catch him. So computer vision, it's not just RGB or this visual domain, right? Even if you have thermal stream, that is also computer vision. All right, so what you can do is if you have a thermal stream, you can easily detect that person. It might be hard for humans, but AI algorithm can do that. So I think they were able to find him, and then so you can see like this is a very real world example, right, where computer vision can play a very, very important role. So I think most of you said like, okay, what problems are involved, which is pretty good. So this was lecture 1, and I will cover some portion of lecture 2 as well today, and we will continue that later. But before we do that, any questions from this lecture?